Hello. In this video, I would like to share formulas to compute two values commonly used to analyze probability distributions, the expected value and standard deviation. In the mathematical world of statistics, there are many ways to analyze probabilities, and some students spend years learning them and their intricate nature. At this point, we take a simple look at these two measures. The expected value, or mean, of a discrete random variable describes the weighted average of the possible values that a random variable can take. Rather than computing the simple average of the outcomes, the weighted average takes into account the probability of each event occurring, thus providing the expected value or outcome of an event. The lowercase Greek letter mu is commonly used to identify the expected value, and it is calculated by summing all of the products of the possible outcomes and their probabilities. The uppercase Greek letter sigma is a symbol that indicates repeated addition in mathematics. And the probability notation here indicates the need to multiply the outcome and the probability for each possible outcome in the distribution. Let's jump to the bottom of the worksheet to see this example. The first two columns of this table show the same results from other lessons, indicating the possible outcomes and probabilities of rolling each outcome with a pair of fair dice. The third column heading indicates we should multiply x, the first column, by the corresponding probabilities in the second column. Take a moment to multiply these values. For simplicity, round your answer to 2 decimal places. Pause the video now and resume playback in a moment to check your work. At this point, you have computed the product necessary to identify the expected value. All that's left now is to sum them together. By definition, the sum of the products of possible outcomes and their probabilities yield the expected value. Therefore, we can say that the expected value, or mean, of rolling 2 fair six-sided dice is 7. Now we will go back to look at standard deviation. This allows us to compute how far other measurements are spread out from the expected value. A small standard deviation indicates the expected values to be close to the mean, whereas a large standard deviation indicates the expected values to be distributed further from the mean. As mentioned before, some students spend years studying tools to help analyze probabilities. However, the more you practice with these two computations, the better you will understand the meaning of each. The lowercase Greek letter sigma is commonly used to identify standard deviation. You might notice that this formula looks similar to our last formula. A series of values must be summed, but we must square the possible outcomes before multiplying their probabilities. Then, with the sum found, we will subtract the square of the expected value we found a moment ago. If we were to only compute this result under the square root, we would have variance, another statistical value. However, completing the last step of taking the square root, we will compute the standard deviation. Take a moment to compute the last column of our table by first squaring the value from the first column, then multiplying by the corresponding value from the second column. Again, for simplicity, round your answers to 2 decimal places. Pause the video now and resume playback in a moment to check your work. The sum of these values is not the standard deviation. Rather, we must square the expected value, subtract this number from the sum, and finally take the square root. Further study of standard deviations and normal distributions will shed more light on what this value implies. But for now, we can use it to describe the spread of data. While the number 7 is the expected value of this probability distribution, we know that it won't necessarily occur most often during a set of trials. The standard deviation gives us a mathematical description of where most of the results will occur in a series of trials. In fact, if the random variable in a trial was continuous instead of discrete, almost 70% of the trial outcomes should exist one standard deviation above and below the mean. And about 95% of the trial outcomes should exist between 2 standard deviations above and below the mean. If you are curious about this concept, I suggest you search for more information on the standard deviation of a normal distribution in a textbook or online. Good luck.